Welcome to clinical chemistry. We are just going to be talking about the basic principles that a lot of our chemistry analyzers use in the lab. There is going to be a little bit of physics in this lecture, but they're not anything super complicated. And I'd be really doubtful if you got any majorly difficult questions on the physics behind the principles. What I just need you to understand is the components that make up each of these laboratory methods. I just need you to understand how something could affect the techniques or the each of these principles, and associate on a basic level as to what is used for what kind of measurement or analyte that we're looking for. These are the objectives for today. If you are able to fulfill these objectives, then you should be fine for this lecture. So we're talking about methodologies that are used by chemistry analyzers and instrumentation in the lab, and there's a whole variety of methods and principles that we can work off of, and hopefully by the end of this lecture, you'll be an expert on a few of them. So electromagnetic radiation, a very fancy way of saying light. Light is photons traveling in waves. So they don't go in a straight line, they don't go in a diagonal, they go in waves. The intensity of that light or the wave or the radiation is determined by the wavelength or the distance between each crest in a wave, or the highest peak. If we get a shorter wavelength, we're packing more energy into a tighter space. Therefore, not only is it a higher frequency, but it is also at a higher energy. Likewise, the longer a wavelength is, the lower we're packing into a small amount, and therefore the lower energy it is. Um, that's why you'll see like for radio waves, you use that for a lot of long distances because of how long that wavelength is, it is able to travel across a greater amount of distance versus x-rays. We're not doing x-rays to people from like 20 feet away. It's always going to be right close to the patient. So if you could just think of it that way, that might also help. Or just following this diagram would also help as well. Now, it is described on a spectrum. We're not going from point A to point B. There's no predefined set. When you look at visible light, which is sort of where this is, you can see that it's a smooth transition because it is a spectrum. It's not just one point to point B. It is a gradient. Wavelength helps describe where we fall within this spectrum. So light is the UV invisible portion of this giant spectrum, and you see that it only makes up this much of the spectrum. Beyond that is invisible to us human eyes. Animals can see UV or infrared depending on what they have, but for us, visible light only makes up this much. So another definition I want you to be familiar with is called transmittance. Basically, it's describing that when light passes through some sort of absorbent substance, the intensity of the light following passing through that absorbent substance is reduced. Therefore, transmitted intensity will always be less than the original intensity. If you think about curtains, right? Like what do we use it for? We use it to block out light that's coming in through the window. When we lower our curtain, it's forced to pass through the curtain, and the light that gets transmitted through the curtain is reduced. So, you know this concept in daily life, but it makes up a major part of our this whole concept here basically describes how we measure stuff. So, um, transmittance is this formula here. We just replace the original intensity with the reference solution. By the way, if you see any sort of reference solution, it contains everything that is not of the compound of interest. Usually it's like water or something like that. So we can convert this ratio into a percentage transmittance. Then using that percentage transmittance, we can then plot it out into this. So when we take cuvettes that are of equal length, equal witness, and full of an absorbing material that is of the same concentration, each cuvette will absorb the same fraction of energy that we were talking about before. Percentage is just the same way to describe it, just in a percent. So when we graph this out in the relationship within the number of cuvettes or the length of light traveled versus transmittance percentage, we get this logarithmically decreasing curvature here. This relationship is called Lambert's law. Just to put it more explicitly, radiant power decreases logarithmically as light path increases arithmetically. So you just, in plainer English, the longer that light has to travel through these cuvettes, the more that transmission will decrease in a logarithm, or this curvature that you see here. It's not a straight line, it's a curvature. Now you might be wondering, okay, like this is great. What do I use this for? Well, we can then use this Lambert's law. And if we convert it in a way that allows us to get to this linear relationship, then it becomes a lot easier to work with. If any of you know a little bit about statistical math or like a little bit about math overall, it is a nightmare to try to calculate anything along a curvature. Computers can do it, but even then, it's not a great way of doing things. So we'll take this relationship and use it to calculate absorbance, or the how much light is absorbed into the cuvettes. So in a single cuvette of fixed width, transmission will decrease exponentially with an increase in concentration. As transmission will decrease, absorbance therefore must increase, which makes sense. When you are transmitting less light, you are absorbing more of it. So when we take our measured transmittance values, we then can convert that into this formula here, which becomes a very nice linear relationship. No more are we dealing with curvatures. We are now able to plot concentration against calculated absorbance. So we're going from this awful, awful curve here to a very nice straight line. Um, So, this linear relationship of where it is absorbance plotted against concentration is called Beer's law. Beer's law states that absorbance is directly proportional to the concentration, light path, and distance traveled. Big A for absorbance, equals ABC. Um, which, if you remember from any sort of algebra class, makes up a very nice linear path that has no intercept. So it's a very nice and direct, easy way to be able to calculate concentration when we get this relationship from absorbance. So overall, to get from Lambert's law to Beer's law, we must measure transmittance to help calculate absorbance. And this is a point that I have to stress: absorbance is never directly measured, it is calculated. When we get absorbance, we can then use that to calculate concentration. And that is exactly how literally every single math that your instrument is doing works off of, if they're using light spectrum as its methodology. But this isn't a relationship that's true across every single reagent, analyte, instrument. We have to establish this relationship first in order to be able to calculate concentration. I can't just pick a calibration curve for that measures for sodium and apply that to potassium. They're two different things, and because they have two different reactions, so I have to establish the relationship. This relationship is established through what we call calibration. Calibration just basically means that we are trying to generate this Beer's law in order to calculate the concentration of whatever it is that we're measuring. In order to establish calibration, we must set up calibrators, or samples with known concentrations. We must then also have two or more calibrators, because if you ever try to generate a graph from one point on a graph, that ain't happening. So we do need two or more levels of calibrators. Because we know the known concentration of each calibrator, we then know it must lead to a specific absorbance. When we know that, we can then plot this absorbance versus the known concentration of the calibrators. And when we get this plot, we will then take the calibration constant, which is the slope, and that is then used to calculate the concentration of any unknowns or your analytes. In a really perfect non-physical world where we are just dealing with pure math and no nonsense that happens from living in reality, a perfect and ideal calibration will have a slope of exactly 1 and an intercept of exactly 0. But, real life doesn't really work that way. And this is sort of the biggest thing that real life kind of screws with is Beer's law stops working when our absorbance values are greater than 2. What happens is when Beer's law is no longer being obeyed beyond 2, when you plot out the absorbance, it starts looking like a curve. It goes straight, then suddenly starts plateauing. Um, this is just due to the way that light bounces off of other things, and that kind of messes around um, when you have this large amount of particles suspended in a liquid. So when we go beyond 2, then you result in a nonlinear relationship. And like I mentioned, that is a nightmare to try to calculate off of, especially when it plateaus like that. So because of this, manufacturers have determined lower and upper linearity limits. So basically, within a certain amount of concentration, the manufacturer says that this measurement is accurate. If we go below or beyond that, then we can't really say that it's accurate anymore, unless you do a dilution. When you dilute something, you lower the actual concentration of the sample, and therefore we fall within this lower and upper linearity limit. And that's the purpose of doing a dilution in clinical chemistry. Um, the biggest thing that we have to remember, though, is once we dilute something and get a calculated result from it, then we must also apply the dilution factor applied to the sample. So if I diluted something by 2, I get a measurement that looks about that. Then I get a measurement, and then that measurement I have to multiply by 2. All right, so that is literally the entire principle of how everything that involves light that I'm going to talk about works moving forward. Um, if you didn't quite catch that, then I would recommend either reading the slides again, maybe at your own pace, or trying to find other resources that explain it a bit better. But just understand that we have to get from transmittance to absorbance to then be able to calculate concentration, which is along this linear line here. So, spectrophotometry and photometry are probably the two most common methodologies that you're going to see in the lab. We're going to use specific wavelengths to measure specific things. And the way that we isolate specific wavelengths is either using prisms, which is like a crystal prism, whenever you see like the way that rainbows can form out of the glass, that's what a prism is, or filters, which their purpose is to absorb whatever light wavelength that we don't want and just allow the isolated wavelength that we do want through. The spectrophotometer is made up of five basic parts. Like, again, anything that uses spectrophotometry will use these components. So first, we need some sort of energy source for our light. So that could be a bulb or a lamp, which provides a polychromatic energy or just multiple colors. Because if you remember from physics when you were a kid or back in college, white is made up of all the wavelengths. So, in order to get to a specific wavelength, we must have a specific wavelength selector. Again, that could be a prism or a filter to obtain one color light that we want. We then pass that isolated wavelength through a cell or a cuvette, which contains our sample, which then allows that absorption that I keep talking about earlier. Whatever the transmitted light passes through is then picked up by a photodetector, detects light. This will generate, amplify, and digitize the signal, just basically saying that we go from light to a signal that our instrument can read. Then, last but not least, that energy signal that that is generated from the photodirector is then displayed out onto some sort of readout device. It just basically we can't read electricity with our eyeballs, so this is our way of being able to look at it. Usually, it just means a computer. So, if we want to get a little fancy with it, we can either have simple or dual beam spectrophotometers. So, simple just means we have um, one path into the detector, but we don't really have a reference to go off of. Like, how do you know if the light around you is being affected by other factors, or how do you know that the filter is working, or if it's dirty, or anything like that? Then we can pass it through a dual beam, so the light will still go through, but now this light will not only just pass through our sample, but also through what we call a reference cell. When we get this reference cell, we can then determine the difference between our measured sample and our reference, and that will allow us to correct for a more accurate concentration. So, a few two common-ish light sources that we use. I've only really seen incandescent light bulbs, literally just the same light bulbs that you have in your house. We use that for a light source. It's usually a tungsten light bulb, um, though it's not a lot of energy if we're trying to go at a super high wavelength. I mean, you've seen lights in your house. I hope to God that they're not cooking you when you're living. But we can choose between a continuous um, incandescent lamp or a line spectrum. I don't really know the nuance between picking either one of these, but for lasers, which by the way is an acronym if you didn't know this, and this is the full one. I do not expect you to know this. This is just a fun fact that you can pull out on all your friends. But lasers help us get to this higher energy wavelength if we need to because it's so intense. So it just focuses a bunch of light into one single focused non-divergent beam. Non-divergent meaning it won't go any in a random direction. It just goes at one wavelength in a very intense output. Um, and we'll use this if we need higher wavelengths. But again, most chemistry analyzers I've seen use an incandescent light bulb. So for spectral isolation, like I said, we have two options. We could pick either between the filter or the prism. Filters, which is going to be our most common, which will absorb any light that we don't want and only allow the one that we want through. So you can see through this absorption filter, white light is coming through in all of these different spectrums, but we only want the green. So we put out a green filter, and that will only allow green light to pass through, or at least at a greater um, length than the other. We can choose other interference filters. They could be UV, visible, infrared. just providing some sort of optical interference. Or we could do prisms, where when we angle it just right, we only get the light that we want at a specific angle. And you'll often see that they'll have these like diffraction gratings. Basically, we just split the wavelength in through very small spaces, which then split it into multiple beams. So that's kind of cool. Cuvettes are just anything that's a clear container that holds liquid sample and reagent for analysis. Most of them are only going to be 1 centimeter because in order for Beer's law to work, and also it's just the easiest length that we pick, it's going to be the easiest to plug in into Beer's law. We can choose different materials for different wavelengths. So if we're trying to go for a higher energy, then we're going to opt for our quartz crystals. If we're working at a lower energy reaction, then we're just going to use borosilicate, or just it's almost like fancy glass or plastic. Plastic we can use for UV and the visible region of light, but they're usually disposable, and also, but and unlike the quartz crystals or the borosilicate, we can't keep reusing it, because if you ever had interacted with plastic in your house, you know that they can scratch really easily. Solvents will often want to react with plastic. Cleaning is a nightmare. I mean, again, if you ever try to clean clear plastic to try to keep it clear, then no matter what you do, it's going to end up scratching it up, and it's a cheap enough material that we'll just use it once and then toss it away. um, for a reference blank, we're going to put in clinical reagent water, because that should lead to an absorbance of 0, assuming that there's nothing in the water. Photodetectors, literally all it does is just convert the light into an electrical signal that is directly proportional to the number of photons. Basically, its job is to make sure that it reflects the amount of um, light that passes through into it and generates an appropriate amount of signal that way. Um, Photodiodes, which is this little bit here, what happens is when light gets absorbed into it, it'll generate electrical currents. I don't really know the specifics behind that, but that's all you need to know that it does. And if we are working with something that has a really weak light signal, then we could use a photomultiplier tube. Basically, when we get light to start bouncing against surfaces a bunch of times, it'll start increasing its wavelength. So that way we can get to a higher energy, and that is a stronger signal that our photodiode can pick up. When light is too weak, then it doesn't really do a good job at detecting it. Um, all right, so that is the basic parts of spectrophotometry. We can also use reflectance photometry. So basically, the measure of light that is reflected off of the reaction mixture. So usually the intensity of that light signal is compared to some sort of reference surface, like usually like a blank white square, and we can either choose to use a polished surface or a specular reflection or diffuse non-polished. I don't really know the nuance behind either, but just understand that they can exist. But what's really cool is you're more likely than not have seen reflectance photometry. You know these UA dipsticks here? Yeah, when you dip them into your urine, they change color, and based on the way that that color changes and is reflected by the light that reads out, then we can determine the chemistry results. So what happens is light bounces or goes through a filter, bounces off of one of these urine pads here, then that light that is reflected off of is picked up by a lens and turned into a result that we can read. Um, if you work with the Vitroses or orthochemistry analyzers, then they do a very similar thing, except we just use these dry chemistry slides here. Once we inject them with the liquid, then a reaction is going to form, and that's going to cause a color change. The intensity of the color that is changed when once the reaction is done is determined or is directly proportional to the concentration. So, very similarly to spectrophotometry, reflectance photometry still has some sort of polychromatic light source, some sort of like monochromator or just filter to help isolate one wavelength. That wavelength is then passed through a slit to make it much more concentrated and making sure that it goes in one direction. Then that bounces off of some sort of reflective surface. That light that bounces off of the reflective surface is then concentrated by a lens. When that goes to the lens, then that's picked up by a photodetector and that's read out onto a device. All right, so that's all we'll talk about light. That's basically what you'll see most of the time in chemistry analyzers, and you probably have seen it already at a basic level, you just didn't know it. Now we're going to talk about energy levels. Um, Energy levels are distances from a atom's nucleus where an electron can get found. As electrons get further away from the nucleus, their energy will increase. In order to jump from one energy level to the next, electrons can then absorb energy. That energy gets put into them, and then they can jump over into a higher energy level. Likewise, if they want to drop down from a higher energy level, they'll release energy via light, and that'll drop them back down to their ground state eventually. So basically, what'll happen is some sort of energy gets deposited into the electron. The electron will jump all the way out here, and unless that source is continuously fed to the electron, that electron will eventually bounce back down to its lowest energy level or ground state. Um, you can either choose to visualize it like this, or we have a little diagram here. I'm not sure which one's easier for you to use, but just understand that we can feed electrons energy to make them bounce up higher, and if we don't keep feeding them that energy, then they'll eventually go back down to ground state. So we use this in what we call atomic absorption spectrophotometry. This is a optical method used for trace metals like lead or nickel in any samples. Or not nickel, sorry, zinc. So the steps that we need in order to do is first we must nebulize the analytes. So we just turn them into a bunch of atoms, and those atoms are brought back down to ground state. In order to be able to nebulize a sample in the first place, we'll vaporize it um, either through flame or flameless methods. Then we produce a hollow cathode lamp specific to that element of interest. So when we produce a wavelength that is specific to that element that we want. The element that we want, or that will then absorb the energy, which will um, decrease the light beam intensity. So basically, the idea is that atoms and ions can absorb light at a specific unique wavelength. Um, the radiant energy is measured by a detector. The amount of light absorbed can be determined, and once we determine the amount of light that is absorbed, then we can calculate the concentration. Really important point is that atomic absorption is really specific to the element being measured because atoms can only absorb light at that specific unique wavelength for them. Now that being said, it is highly specific and highly sensitive, but if something resembles that um, element just enough, then we can lead into false positives. So anytime that you see some sort of atomic absorption done, it's usually going to be very, I don't really know how to say it other than chemically sterile. We're not keeping bacteria out per se, but we're trying to keep other elements that would look really close to that metal that we want out of the space. It's a really complex procedure. Um, we get a little worried about nebulization if the sample is too viscous or too dense. It's really time consuming. And it's also really labor intensive. If a lab has atomic absorption, then they're gonna be making sure that you're very technically competent, making sure that you're able to run not only just run the analyzer, but making sure that you're able to keep that space clear of any contaminants that may cause false positives. And this is how that breakdown works here. Fluorometry is the measurement of emitted fluorescent light. So this will measure the concentration of solutions that will contain molecules that fluoresce. Um, Glow, I think, is probably the best way of phrasing it. If you ever seen um, like any sort of UV black light party going on and everything starts glowing, that's what's happening. So this will happen when a molecule absorbs light at one wavelength and then re-emits light at a longer wavelength. Um, we'll often use UV radiation as a source for excitation, and the emitted light that is emitted is directly proportional to concentration. It's very specific and much more sensitive than absorbance is. Flow cytometry. You will be talking a lot about this in other classes as well, but it's the process of forcing cells into a single file line that pass through this light source. So it's a solution of cells in some sort of fluid stream. When that light bounces off of that cell as it's passing through the single file line, then light gets scattered either forward or off to the side. Knowing that, we can then classify and the size and the shape of the cell via light scatter. We can also add in fluorometry to make it even more specific. So we can add markers to each of these cells. So not only can we classify it by the size and the shape, we can also get more specific by determining the inner complexity of the cell, how much lobing or I guess parts of a nucleus appear, and the cell surface structure. We could graph this all out into this graph here based on the relationship of everything that we just talked about. It's pretty cool. You'll learn more about it in hematology. That's usually where it pops up the most. Lumometry is those glow sticks that you see. Again, different than the UV fluorescence, but it's the biggest difference is that the um, glowing is generated by some sort of chemical, biochemical, or electrochemical reaction. At the basis, it's some sort of chemical reaction. So we're not injecting something with light to excite it into a higher state where the reaction that happens causes some sort of illumination. So we can measure the emitted light as the atom's returning back to its ground state. Um, well, you'll hear the word luminescence, and the specific method of how that luminesces is tied to that word. So if it's luminescence caused by a chemical reaction, then we'll say chemiluminescence. If it's a biological reaction, then it's bioluminescence, and you can figure out the rest from there. So we'll measure this with a luminometer. And the light intensity is directly proportional to the concentration. Chemiluminescence is a chemical reaction with some sort of compound. Bioluminescence is usually by a enzyme or photoprotein. And electrochemiluminescence is an electrode shocks that and that causes the glowing there. Turbidimetry is the measure of just, well, I don't really know how else to say it, turbid something is, or the measurement of the reduction of light due to the amount of particles suspended in a liquid. So as something gets more turbid or more opaque, then that will decrease the intensity of light as the beam passes through the solution. This measures the scattered light that passes through after as each of the light bounces around with these molecules. Remember that for this one, scattered light is always equal to the incident light or the light that hits it. We can easily perform this with a spectrophotometer, just placing a detector at 0 degrees or 180, just basically in a straight line like this. And it is impacted by particle size and concentration. Nephelometry is similar, except it's measured at a angle instead of 180. As long as it's not placed at 180, as long as the scattered light is measured at not in a straight line, then it is considered nephelometry, but usually the angle will be measured at 90 degrees. The amount of light scattered is again still proportional to the concentration of the analyte. Unlike turbidimetry, which is only impacted by particle size and concentration, we now have to worry about wavelength, particle size, and concentration with nephelometry. So if we place it here, then this is turbidimetry. If we place it anywhere that is not in a straight line, then it's nephelometry. Refractometry, you might see it really old school method to be able to measure specific gravity in urine. Nowadays, it's more so being used if you brew alcohol, I guess. It's a quick and easy way to be able to measure the concentration of something in a uh, thing. So we use the principle of light I always say this word wrong. Refraction as it passes through different mediums. This when the speed of light changes, then that causes a change in direction or angle. Then where that light hits along this measuring tape or measuring tape, this measurement here, then we can read the whatever it is that we're looking at. Again, it's usually specific gravity for our case. All right, and that's it for all our light-based methods. Spectrophotometry is, again, by far the most common, but you are expected to know each of the methods that I described and the differences between them, and remembering the principles from Lambert's law to Beer's law and um, ab- how transmitted light affects absorption, which then affects our concentration calculated. So we're going to talk now about electrochemistry and chemical sensors. Um, these are all based on, well, electricity. So in a electrical chemical cell, we have what we call these two half cells and some sort of salt bridge here. Each half cell, which is these things here, contains one electrode, which is either a anode or a cathode. Cathodes will attract cat ions, which are positive, so cathodes are negatively charged. Anodes will attract anions, which are negatively charged, so anodes are always positively charged. It's kind of confusing. I always kind of screwed these terms up when I was a student. Just understand that opposites attract. So if you know that a cathode is supposed to be attracting cations, then it has to be negatively charged. I think there's silly other ways to be able to memorize it on the internet, but I'll have to look those up for you guys. So these electrodes are then immersed into a salt solution. Um, Either we'll have a salt bridge or we can just have that salt solution also serve as a salt bridge by just connecting these electrodes here. Um, Either way, we just need something to connect these two cells together. So what happens is electrons will naturally flow from an electrode with a lower electron affinity to a higher electron affinity. So we're going to do a redox reaction. So it'll go from oxidation to being reduced. And this chemical reaction will continue until one of the chemical components is depleted. Potentiometry is used a lot in blood gas analyzers. That's what you'll see it the most for. These will be used to measure pH, CO2, or electrolytes. Though I think I have seen a lot of chemistry analyzers also using it for the electrolytes as well, potentiometry, I mean. So pH, we're going to use a glass electrode that is only sensitive for hydrogen ions. For PCO2, we're going to modify that glass electrode, making a membrane just for PCO2, and is then immersed in a bicarbonate solution. And electrolytes, we're just going to use ion-specific electrodes for that specific ion. So what happens at potentiometry is it measures the potential difference between two electrodes in an electrical chemical cell to determine concentration. Um, Basically, we're just measuring potential. We're measuring basically how strong of a difference between the two reactions are in order to get to our concentration. Electrical chemical cells are made up of an indicator or a measuring electrode and a reference electrode, which is measured by electrolyte solution, usually the sample. The electrode is just a single metallic conductor, and again, we're using these half cell voltages, or we're comparing these half cell voltages. Common reference electrodes is calomel. I always say it wrong, but it's mercury binded with chloride or silver chloride. So we have this glass electrode here that's specific to pH, um, where this tubing is filled with HCl or silver reference here. So the exposure at the end here allows the sample to exchange hydrogen ions between the two sides. This this exchange creates potential between the outside and the inside, which is measured, and that's how we get to our concentration. We have to calibrate by comparison with standard buffers with some sort of known pH. That way we know what we're measuring is accurate. pH readings, by the way, are super temperature sensitive. We have to calibrate and read at 37 degrees Celsius to make sure that it's accurate to our human body. 37 degrees is the typical temperature for a human body. PCO2, again, very similar setup, except we're just looking for CO2 gas. So our solution that we're going to soak it in is bicarbonate instead, which is then combined with a CO2 permeable membrane. What happens is CO2 will want to pass through the membrane and then reacts with the bicarbonate to form carbonic acid, which decreases the pH. The pH that is at the end of this reaction will be inversely proportional to the PCO2. Um, Hydrogen concentration is also proportional to CO2 just by the nature of how pH is done. But just understand that pH is inversely proportional to PCO2. Ion selective electrodes contain a specific membrane for that specific ions. So we have what we call an ionophore is placed into the membrane. Just basically, it's a thing that attracts the ion. Obviously, we use different ionophores for different ions, and the driving force is the concentration gradient. So we'll go from less concentration, we'll go from a higher concentration to a lower concentration. Then when that happens, the attraction brings this system to an equilibrium eventually, and that voltage differential is measured. This is something that you'll need to know. I'll just say it right now. The more complicated the name is, the less likely it is that you're gonna need to know it. But know that we need to know which ions is the component, or sorry, the key membrane component or the ionophore only attracts with that specific ion. So, for example, if we want to measure sodium, then we're going to use silicate suspended in glass. If we are going to measure potassium, then we're going to use valinomycin, not vancomycin, valinomycin. Voltammetry or amperometry is the measure of the current produced through a redox reaction, an electrode, using some sort of external voltage source. So we're going to be powering it with some form of electricity that's outside of the reaction. So we'll use it for the partial pressure of oxygen or PO2 in blood. So the PO2 electrode is a platinum cathode with silver anode immersed in some sort of buffer. This membrane separates the electrodes from the sample. If there's no oxygen, then current does not flow, but when there is oxygen, oxygen gets reduced at a platinum cathode using the electrodes from the anodes. That difference then generates a current directly proportional to the PO2 concentration. Conductometry is a determination of an analyte quality measuring its conductivity, or how well can it pass electricity through itself between two different inert electrodes. So these electrodes are not active. What we're trying to see is how well can something conduct energy. So you'll see this a lot for hematocrit. So plasma will conduct electrical current because water will also conduct electrical current. But the red cells act like insulators. They're not so good at conducting electrical currents. So what'll happen is that when we're at a higher concentrate or a higher hematocrit, that will be a larger proportion of RBCs, which will reduce the conductance or ability to conduct electricity. Sort of the big issue though with using conductmetry in measuring hematocrit though is that high proteins will decrease conductivity. So more likely than not, you're gonna see it used for electronic cell counting or Coulter or impedance. Basically, we get a solution of cells that pass through this really small aperture here. On each side of the aperture, we have electrodes on either side. Each time that a cell passes through that aperture, it causes a change in resistance. When each time a change in resistance is detected, then that counts. Then the analyzer is able to count each time that resistance changes. So it's a really efficient way of just if you literally are just aiming to count the number of things, very simple, very neat, and that's what we really like in chemistry and hematology. Coulometry is the measure of electrical charges passing between two electrodes. So the charge will be transferred between both electrodes. Um, Comparing this to voltammetry, which we just talked about, which is only the change that happens at one surface of one electrode. So the amount of charge that passes in between these two electrodes will be directionally proportional to the redox reaction, and we'll use this the most in order to determine chloride or chloridometers. Speaking of which, so this is basically the method that we used in order to determine how much chloride is something in there. So we'll use this for so we're going to use a silver anode versus a platinum cathode. The constant current will produce silver um, I, ions and hydrogen gas. Silver ions will be released at a constant rate, so that way we can titrate it with chloride. When chloride is present, it'll then react with that silver ion, and that will cause silver chloride to precipitate out, which will reduce the ion. When we saturate entirely all the chloride, that will cause a sudden increase in silver ions. That's what we mean when we say titration. So the moment that we figure out that there's a large amount of silver ions detected at the measuring electrodes, we can stop the reaction in the time that it takes to go from basically zero excess silver ions to all of them, then that's what we use to calculate chloride. The reason that chloride is so important is because we use it to measure for cystic fibrosis. We'll talk more about it later in body systems, in the later body systems lecture, but understand that we use this to um, diagnose for cystic fibrosis. Chemical biosensors is just some sort of chemical sensor that uses some sort of biologically sensitive element, which is combined with a chemical transducer. When that happens is when a biochemical signal is generated, that gets converted into an electrical signal, and that's how we can use to be able to determine the concentration of something in whatever that we're testing. So we'll usually use some sort of biological element. Usually it'll be enzyme based, um, which will help catalyze the reaction, or we could also use binding affinity based um, biological elements. But the role of either one of these is to help recognize the presence, activity, or concentration of what we are measuring. Our transducer will usually either be amperometric, conductometric, or optical. Basically, its job is to convert this biological signal into some sort of electrical signal that we can then measure out and read. So the most common one is a glucose biosensor. So this is based on enzymes that have a amperometric detection. So what'll happen is the enzyme glucose oxidase will bind to oxygen and produce hydrogen peroxide. Hydrogen peroxide is then detected via oxidation at some sort of platinum electrode. This is what we use, when you get your finger sticks done if you are diabetic or know somebody who's diabetic. This is what we use. And that's the end of this lecture. It's a little dry, and just because it's based on a lot of talking about physics and talking about chemistry, but it is an important thing to learn. And once you sort of get the gist of how these things actually work, then you'll be able to understand this thoroughly. So try to understand the components of each methodology, try to understand what we use it to measure it for, and the principles that each of them are based off of. And this is your homework. Please submit if you are my student, if you're one of my students.